you're a geologist, kimberlites are some of the most exciting things you can find, but not because of the stones themselves. What geologists are really after is what's often inside them. Diamonds. Kimberlite rock formations are actually the leftovers of particularly explosive volcanic eruptions. They form when a column of the fastest magma on Earth bursts through the thick crust of a continent, leaving a large crater on the surface. We've found more than 6,000 of these formations, and they're on every continent. But the strange thing is, no one has ever actually seen one when it's happening. So why don't kimberlite eruptions seem to happen anymore? Well, a recent study suggests that these volcanic bombs just have a very long fuse. Kimberlites get their name from where they were first discovered, near the city of Kimberley, South Africa. The term kimberlite refers to both this unique type of eruption and the rock it creates. The eruption begins over 150 kilometers beneath the surface in the asthenosphere. This is the region of the Earth where rock that's mostly solid can flow like a liquid. Magma begins to rise from this region through fissures and cracks in the lithosphere, the rigid outer layer of the planet. As it rises, substances like water and carbon dioxide turn to gas and expand, widening the cracks in the lithosphere and accelerating magma's ascent. It also vaporizes any groundwater reservoirs it runs into, which further powers the rocket of magma. It rises fast, up to 20 meters per second. And there's no chamber that the magma hangs out in beforehand like it would in other kinds of eruptions. So kimberlites are the fastest trip from the asthenosphere. The journey ends in an explosive eruption with lava bursting through the surface at up to 200 meters per second. This leaves a large crater in the ground above a column of kimberlite rock, known as a kimberlite pipe. It's made of a dark, often green-colored rock with large crystals in it. And yes, sometimes those crystals include diamonds. The diamonds don't form in the kimberlites, though. They just hitch a ride with them on the way up. They come from the diamond stability field, where pressures and temperatures are high enough to change carbon into diamonds. It's more than 100 kilometers beneath our feet, but because kimberlites are an express elevator between these depths to the surface, they're our main source of these gems. Around 10% of kimberlites have diamonds in them, but when you're talking about something that can fetch a price as high as diamonds, those odds are high enough to get geologists very excited. Despite more than a century and a half of geologists looking for and studying these structures, though, some pretty big mysteries persist to this day. The first mystery has to do with where we find these kimberlites. See, they mostly show up in the middle of continents in regions known as cratons. Cratons are the stable cores of continents that have stood strong through many cycles of supercontinents being built and broken apart around them. They've stuck around as intact units for the last 2 billion years and are underlain by thick cratonic keels. These are massive roots of mantle rock that make the lithosphere up to 350 kilometers thick in these spots. So the fact that an eruption of any kind is able to punch through that normally stable layer is really weird. And the second mystery is about when kimberlites happen, since the vast majority are tens of millions of years old. The most recent one happened around 10,000 years ago in Tanzania. That's pretty recent in geological terms, but it appears to be an outlier. All the other kimberlites we know of are at least 30 million years old. Researchers have looked into this before, and they found that the ages of kimberlite eruptions aren't random. Kimberlites come in pulses that peak around 30 million years after a supercontinent breaks up, which is weird because a continent breaking up is a really geologically active time. So it seems odd for these eruptions to wait for 30 million years after the party ended to make an appearance. And besides, we see these eruptions in these stable cratons of continents, in the areas that are literally defined as where a continent isn't breaking up. For a while now, the leading idea linking continents breaking up and kimberlites was they are both caused by mantle plumes. These are buoyant blobs of hot, partially melted material which can rise up and wreak havoc on the surface. Mantle plumes cause lava to basically flood the surface of the Earth. Now, there are already strong links between mantle plumes and continents breaking up, but we've been less sure about whether these plumes could also be fueling kimberlites. Researchers considered this idea, but when looking at the ages of those large igneous provinces that we know are linked to mantle plumes, they noticed that they tended to erupt before continents broke apart, not after, like kimberlites do. And the mantle plume idea doesn't explain the pattern of kimberlite eruptions slowly migrating away from where the tectonic action is. But a 2023 paper may have helped fill in some of the holes in the mantle plume theory when they found a link between the breakup of a continent and those deep cratonic keels. See, when a supercontinent begins to break up, it forms a continental rift. The lithosphere thins out at this rift as the continent pulls apart, and hot material from the asthenosphere rises upward to fill the gap. That destabilizes the asthenosphere below it, and it begins to convect, meaning the hotter liquid is moving upwards and cooler liquid drops below. This convection moves outwards, away from the rift and towards the craton. One convective instability triggers another, and the circulation spreads at roughly 20 kilometers every million years. That is, until the convection reaches the cratonic keel. It erodes material off the bottom of the keel, replacing it with a partially melted mixture of hot asthenosphere and the keel itself. This material then rises up through the lithosphere to form the beginning of a kimberlite eruption. So the rift of a continent is the initial trigger that lights the fuse for kimberlites to erupt roughly 30 million years later. We can see evidence for this in the timing of kimberlite eruptions. Those closer to a continental rift erupt sooner than those further away, tracing the movement of the asthenosphere convection below. It's a promising theory, and it may help fill in a lot of the confusion around how these kimberlites form. In fact, remember that weirdly recent kimberlite eruption around 10,000 years ago in Tanzania? This new theory may explain that too. Tanzania is part of a craton, which is just south of the East African Rift, a continental breakup that began 25 million years ago. So the kimberlite was right on schedule for this idea, geologically anyway. And there you have it. That's everything you need to predict where you can strike it rich and discover the next big diamond mine. You just might need to wait a few million years.